you like fell into it.
Okay. All right, so questions? I have your graded problems from the other day, which I'll give you after class. I just checked them and kind of skimmed through them, so you're going to have to look at the answer key to make sure you got everything correct. So a check mark does not mean everything is correct. A check mark means you turned it in. And you don't know when I'm going to do that, so you have to do all the problems every time. Anna or Annie?
I'm just a little confused about how to identify like meso, like same, not meso, like what's a or if there's a trick or like, I don't know.
Like,
Just like being able to like look at a molecule and like it has all the same like a Fisher projection with two chiral centers. And like I was looking at some of your practice like exams and there was one it was same and not it was same in meso, but like you moved some of the molecules, so I didn't understand like when you can move them and you can't. Like, I was just a little confused.
okay, so let's say you had these two molecules, and the idea is to determine are they same not meso, same meso, diastereomers and enantiomers. So if you were going to go through a sort of a process to look at this, and I be honest, I haven't had a chance to think of a flow chart, but my process would start with this. Number one, if it's only one chiral center, it's only going to be same, not meso, or enantiomers. So if you only have one chiral center, that eliminates two possibilities. If you have more than one chiral center, then I, first of all, would look to see if it's meso, if there's a possibility of it being meso. Now, for a Fisher projection like this, the molecule is going to be meso if it ends up looking like that, where you can see the mirror plane through the molecule. In a Newman projection, a meso compound would show up having the front three carbon groups being the same as the back three carbon groups, and you can align it like that in an eclipse conformation. So these are both examples of when a Newman or a Fisher can be meso. So that's what you're trying to set the molecule up as. So the second thing I would do with more than one chiral center is I would look and see, does this have the possibility of being meso? Because if it does, you have to determine for both molecules whether they are meso or not. So when I look at this, I see three groups on the top carbon, three groups on the bottom carbon. They are not the same three groups. Therefore, this molecule can't be meso. Okay, so that would be my second thing to look at. Does it have the possibility of being meso? Then the third thing I want to look at is I want to look at the fact that the carbons are lined up so that I'm going to compare top to top and bottom to bottom, and I'm looking at the same carbon. And in this case, the chlorine is attached to the top carbon on the left, but the chlorine's attached to the bottom carbon on the right. So I've got to orient the molecules so that they're identically the same, unless you want to do R and S. But let's be honest, R and S on this, that's 4 R and S determinations you have to make, and you have to get them all right, then get your connection. So what I would do is I want to line up these two molecules. And what I can do in this case is I could rotate this molecule 180 degrees and then draw the new orientation. As long as you're rotating things in the plane of the paper or of the screen here, the bold and dash wedges don't change. They only change when you flip things. Because when you flip them, it goes from being toward to away. So in this case, I'm going to rotate it 180 degrees. The Fisher projection is going to stay the same. But now my OH is going to be on top, and my H that was on top is going to be on the bottom. Then looking at the CH3 on the upper left, that's going to go from being on the upper left to being on the lower right. The BR is going to go from upper right to bottom left. The hydrogen lower left now to upper right, and Cl going from lower right to upper left. Okay. So now I've got front or top to top, bottom to bottom, they're the same carbons. Okay. So you always have to reorient the molecule so that the carbons are in the same orientation. Okay. Does everybody see that? So now it's just a matter of comparing top to top and bottom to bottom. Are the tops same or opposite, or bottoms same or opposite? And you can do this one of two ways. You can use rotation, you can switch, but you can't do both. So you got to make a choice. Am I going to try and rotate these and line up the groups? If I try and rotate them and line up the groups, if I can line up two groups, either the other two will line up or they won't. If they won't, opposite. If they will, same. So we can try that. So in order to do that, what do you want to rotate? Let's rotate the chlorine up, the OH to the right, and the H to the left. I've lined up the chlorines on top here. Did the H's and OH's line up? No, they will never line up. If I line up the OH's, the H and the Cl won't. So in this case, the top carbon is opposite in configuration. And you could orient this molecule to make them mirror images if you wanted to as well. But usually what we try and do is line up a group. If the other ones line up, it's same. They don't, opposite. So then for the bottom one, what is it? Same or opposite? Opposite. Because in this case, the methyl groups are already lined up and the other two groups aren't. So you always want to take a minute to see if groups are already lined up, because if they are, you can instantly make your, or look and see if you can see the mirror plane, because sometimes that happens. So in this case, the bottoms are opposite as well. So when I have two molecules and both configurations are opposite, that makes these two I heard it. A little more aggressiveness. Enantiomers. They're enantiomers. So both opposite enantiomers, both same. Whether it's meso or not, in this case it would have been not meso. One of each, one same, one opposite diastereomers. Isma.
So you just said that the CH3 is the one that's lined up, but
Yeah.
there could be two lined up. So what's the other group that's lined up?
The whole top. The whole top is lined up, and the whole top doesn't have to have those groups lined up. It's just the whole top is lined up. So this and this are lined up in both cases. So those would be enantiomers. So sometimes you have to rotate the molecule at the beginning to align the carbons, and then you're going to compare carbon to carbon to see whether they're the same or opposite.
Does it matter that the hydrogen and the hydroxide group are like kind of flipped? Can you rotate around that single bond? Is that why it's considered lined up? Because when you rotated just the top with the ClOH and HOs, and you go back to the molecule that's all the way to the left, because your OH is on the left and your
Right, so in other words, what happened was I lined up the two chlorines by doing that rotation.
But it's
That-
okay that the other two are flipped.
That's what makes them opposite. So when you line up two groups, the other two
Say that
groups,
the top is lined up because the CLs are lined
the CLs are in exactly the same position. So the OH, there's an H there, the H and the OH. The fact that they're flipped means they're not lined up and they're opposite. Now, if you want to switch, if you want to do this with switching, you're not going to rotate. So in other words, if I erase all the rotation here, and I just say, okay, how about I count the number of switches that it takes me to go from left to right and line everything up. What am I going to have to do? I'm going to have to switch the CL and the OH, right? If I switch the CL and the OH one time, the molecules are lined up. One time means I've changed they have opposite configurations. So you can switch without rotation. Just count the number of switches it takes to turn one into the other.
Can you do it as RNS, or is that incorrect?
No, you can do it. You can do it as RNS. Except RNS doesn't work with compounds that could be meso. So, in other words, if I had that one and if I had those two, R and S may give me the right answer, it may not. Because remember that a meso compound, if it's meso and you don't verify it's meso is superimposable on its mirror image. So in other words, if it's meso, the RR and the SS will be exactly the same. So if you have two molecules and you look at them and go, well, they could be meso, then R and S may not work. And so then you would have to say, I have to take these molecules and I have to try and see, are they meso, are they not meso? And so in this case, I would take the top carbon and rotate it to try and see if I can make meso. And so in this case, I'd rotate the OH over here, I would rotate the CL over here, and I would rotate the H up there. Is it meso? OH, OH, H, H, CL, CL. The left-hand molecule is meso. Then I do the same thing on the right-hand carbon, the right-hand molecule. Is the right-hand molecule meso? No? Because these two hydrogens are already lined up, and the CL and the OH aren't. So that makes this one not meso. So the combinations that we would have would be for this analysis, you're going to say, okay, let's determine if for each one, is it meso or not meso. If they were both meso, if both of them are meso, then what do you have? The same meso compound. What if you have meso not meso? Then they become, one's meso, one's not meso. Diastereomers. got to be more. You have to be more aggressive in your saying of diastereomers. Because you're correct. What if they're not meso, not meso? You have two choices. Now, if they're both not meso, what you would do then is now you're going to look at top, top, bottom, bottom. You're going to look at those. You're going to look at those two, and so you're going to say, what if both chiral carbons have the same configuration? Then they're going to be same molecule, but we've already determined they're not meso. So it becomes same, not meso. What happens if they both have opposite configurations? That's the enantiomeric pair. So then they're enantiomers. So for molecules that have the possibility of being meso, you have to do it this way. And in this case, like I said, R and S will not necessarily, well, if they were, let's say you had an R and an R, and another R and an R. That doesn't differentiate between are they the same meso or same not meso. So you'd have to do more with the R and the S. It's just easier to go through it this way.
So you're saying, look, check to see if they're meso before you're doing RNS?
Yes.
Okay.
Because if they have the possibility of being meso, you need to go through and make sure that they're not the same meso compound or that they're not the same not meso compound. So you have to it's just easier to do meso and not meso. Okay.
I'm confused about what you mean when you say that if both the carbons have the same configuration. Do you mean within one molecule, or?
I mean, what I mean is comparing top to top and bottom to bottom is what I mean. Because that's how we can determine, like we just did with the other problem, that's how we determine whether they're same enantiomers, etc. Is always compare the two. So in this case, if I'm speedier at determining whether these are opposite or same, then it's speedier to do that than it is to do RNS. And it might be more accurate. It's everybody has a system. But the RNS system may not always work when molecules are meso or not meso.
Is it possible that like the top would be the same and the bottom would be opposite? And then
Well, then basically, if these are opposite and these are the same, they're diastereomers. That's not a problem. The problem is if the top's the same and the bottom's the same, are they the same but they're meso, or are they the same and they're not meso? So then you have to orient the molecule to determine, is it meso or is it not meso?
So should you just like orient the molecule at the beginning and check? Like,
Yeah, that's what we did.
yeah.
That's what we just did.
Is it always going to be a 180-degree rotation?
Oh, well, that was for the other molecule.
Yeah.
Yeah. I mean, for this one, there's only a top and a bottom, so what I did was I just made the top the bottom in the other molecule, so to get it back, you got to rotate it. But you got to rotate it in the plane. Don't rotate it like this, because then the molecules aren't in the same orientation. And if the molecules aren't in the same orientation, and you can't put them in the same orientation, then you have no choice but RNS. And the problem that you'll see on some of the older stuff is if I do this. If I say, what's the relationship between a Fischer projection and a tetrahedron, you have to do RS. Unless you can turn this molecule into a Fischer projection. Which, if you have a model in front of you, you can sometimes imagine how to do that. And if you can see it in your head, you could do that as well. So if I had an A, a D, a B, and a C, I could actually put that in a Fischer projection where A's here, C's here, B's there, and D's there. but I can see that in my head. If you can see it in your head, then you can put in a Fisher projection. Now I can just determine how many switches it takes to get from left to right. Or try and rotate left into right. Or what else?
Can you go over an SN1 mechanism with an alcohol or with a nuclear file?
With an SN1 with the weak nucleophile as the alcohol?
Yeah.
Okay. You want the alkyl halide plus something like CH3OH. Okay. So, weak nucleophiles can only undergo SN1. So, once you see the weak nucleophile, as long as the alkyl halide can form a stable carbocation, we're good. So, this is secondary, can form a stable carbocation. If this was a primary alkyl halide plus a weak nucleophile, it would be no reaction because you can't form a primary carbocation. And weak nucleophiles can only react with carbocations. So we would break our carbon-bromine bond. We would go through a transition state. And then we would go to the final carbocation in that step. And in the transition state, we're always going to show the dashed dotted lines to the carbon bond that's carbon group bond that's breaking. So we're breaking the CBr bond. The carbon's going to be delta plus, and the bromine's going to be delta minus. So that would be my first step in the first step with the transition state. Then the second step is going to be to have the CH3OH, the oxygen of that, add to the carbocation. And so if it adds to the carbocation, we're going to have a dotted line to the oxygen with the CH3 and the OH attached, or the H attached to it. And then that's going to go to form the O with the CH3, with the H with the plus charge as our oxonium ion. And then in the transition state, we show the bond being formed with the dotted line and then our charges. And so our charges are going to be a carbon has a delta plus and the oxygen has a delta plus. So in other words, in the reactant, the product, wherever there's a plus charge, the delta plus goes. Okay, so that's our transition state, so that's our second step. Then our third step is going to be to break the oxygen-hydrogen bond and give that pair of electrons back to the oxygen. And so if I do that, I'm now going to break my oxygen-hydrogen bond as part of my transition state to get me to the final product, which has the O, the CH3, and an H plus. And then going back to the transition state, the oxygen is slightly positive and the hydrogen is slightly positive. So it's going to be a three-step mechanism. The first step, form the carbocation. Second step, have the water or alcohol add to form the oxonium ion. Third step, lose H plus to get the final product.
If we weren't drawing a mechanism for this and just drawing the products, would we just draw like the,
You would just go right to this point.
okay, and then would you have to do like HBr?
You could. I mean, you could put H plus Br minus or HBr, either one. The thing is, I'm going to look at the organic product first. I may not get around to looking at the HBr. So if it's not there, I may not notice it's not there.
So are the carbocations or this like intermediates?
So this is an intermediate, and the oxonium ion is an intermediate. So if I plotted out the coordinate diagram for this, I would start at reactants and go through the first transition state to get to the C plus. Then I would go through the second transition state to get to the O plus. And then I would go through the third transition state to get me to the final product. So the reaction coordinate diagram for this would have 3 transition states and 2 intermediates. Every step has to have a transition state. So if this is a 3-step mechanism, there would be 3 transition states.
SN1 doesn't always have 3 steps, right? Is there another one that does something else?
Right. So an SN1 is going to have 3 steps if it involves a weak nucleophile, which in this case, that's why it has 3 steps. If I replace that weak nucleophile with a strong nucleophile, so in other words, if I said I'm going to take the chloride and I'm going to react the bromide with it, without drawing the transition states, it would have the first step forming the carbocation, and then the second step would be to form the final product.
But for something like that, you'd have to tell us you wanted an SN1, right? Because isn't a strong nucleophile?
Yeah, exactly. I would have to tell you to do this by SN1 because the chart would predict that this would be SN2. It's just I don't have the ability to. It's a hypothetical. This would be a 1-step or a 2-step SN1. So I think last night I linked where something on Piazza where I wrote out all the possibilities, the number of steps, along with sort of a generic mechanism for SN1 and SN2.
So if you're gonna ask a question about SN1 and 1, would you like specifically say that you wanted the E1, or like if there's an SN1 mechanism, you should always do
So mechanisms problems are different. Mechanisms problems are going to be different because I will tell you probably what mechanism to write. A problem where I just said, hey, no. if I said, here, write the or first of all, with this reaction, what I would say is, number one, tell me the mechanism from the chart. Number two, write the possible products, and three, give me tell me which ones are major. For a reaction that goes SN1 and E1, you would write the SN1 product, all the possible E1 products, and then tell me what the major E1 product is. So in this case, I would look this molecule, I would see secondary weak nucleophile, that means SN1 and E1. So I would write down and say SN1 plus E1. Okay, check, you'd get that correct. Then you would say, well, let's write the substitution product. The substitution product would have an OH substituting because the other H is going to pair up with the Br. So I'd form that alcohol, that would be my SN1 product. Then for the E1 product, this is my alpha carbon. There's one beta carbon, two beta carbons. And so I would write a double bond to each of the alpha and beta carbons to form the double bond. So I would look at this and say, okay, let's write the double bond to the first beta carbon. And then let's go ahead and write a double bond to the second. So I would get those two alkenes because I'm basically losing HBr off of that carbon, and I am losing HBr off of that to form the double bond. Of those two, which one would be the major one? Top or bottom? Or same? Bottom? So then you would just either circle that, or you would say that's the major product. And it's the major product because it's the most substituted, which is the most stable. E1 always gives me the most stable product, which is the most substituted one.
Based on the chart that we did, I think maybe 2 class periods ago, it looks like any SN1 is also E1?
Yes. So if you have a chart with an SN1 in it, it needs to be SN1 plus E1 everywhere there's an SN1. What else?
Can you number 29 from like the graded practice problems? These ones.
Number 29. Can I see it? Okay. So which one of, so here it is, and what's the relationship between these? So what would I need to do for this molecule? Do either, and when I say do either, it means both. Do these have the possibility of being meso? No? We all agreed? No? I don't know. I'm not getting a lot of feedback here. Do these have the possibility of being meso? Thank you. No. I agree. No. Okay, so next thing, what should we do? Are they lined up carbon to carbon? No. Now, if you're going to do RNS, you can go and do your RNS. But if you're not going to do RNS, you need to line them up. So a couple of ways you can line them up. You could convert these Newmans into sawhorses or Fishers. Or we could just convert them into another Newman. So for instance, the Newman is this pointing at you. So what I need to do is I need to rotate it so that the back carbon is towards you. So if this is my Newman projection, what I need to do is I need to do one of two things. I can do this, or I can do this. I can just rotate it, or I suppose I could flip it. Either way you do that, the front carbon, the back carbon, which looks like this, is going to look like that when it becomes the front carbon. So the back carbon has two positions, one position down. So when I rotate it, it's now going to look like that with the V. And the back carbon, since it has let's call this a V down, and then this one has a V up. So the back carbon's going to have the V up. The BR and the OH are both pointed up and down. They're going to stay pointed up and down if I rotate it like this. So the OH then is going to be on the front carbon down, and the BR is going to be on the back carbon up. So kind of like what I did when I rotated the Fisher projection, we went from upper right to lower left. We're going to do the same kind of thing here. So the chlorine is in the back right. When I flip it around, it's going to be in the front left. The methyl group is in the back upper left. It's now going to be in the upper right. The CH3 attached to the front carbon is in the lower right. When I flip it around, it's going to be in the lower left. And the hydrogen, lower left, now becomes lower right. So if I convert those two molecules like that, they're now, carbons are oriented in the same direction. So now I can compare front to front, back to back. And the question is always, what are the fronts? Same or opposite? What are the backs? Same or opposite? So when I look at the front carbon, what can I do? I can try and align them, which I'm going to have to do. So I'm going to have to, I'm going to have to try and align them. How about I try and make the molecule look like this? So rotate the methyl group up here, rotate the chlorine down here, rotate the OH there. Let's just rotate the bromine in the same direction. Bromine there, CH3 down, H there. So I just rotated both the front and the back 60 degrees to convert this into this. I rotated, I didn't switch anything. So now they're oriented exactly the same. So now I can go front, now I can go, are the fronts the same or opposite, or are the backs the same or opposite? So what are the front carbons? Same or opposite? Opposite. So the CH3s are aligned, the CLs and the OHs aren't. Now, if you could imagine a mirror plane being between the front carbons are mirror images. So front opposite, back carbon. Bless you. Opposite. So the back carbon's opposite because if you look bromine, bromine, hydrogen, hydrogen, methyl, methyl, the methyls are lined up, the other two aren't. And so in this case, they are also a mirror plane. So the back carbon's opposite. So if they're both opposite, that makes them enantiomers. And if you converted these into a sawhorse or a Fisher projection, you would have to do the same thing. To talk about carbon to carbon, you've got to align them exactly the same way. Why aren't they meso? Because the front carbon has an OH, a CH3, and a Cl. The back carbon's got an H, a Br, and a CH3. The only way it can be meso is if the three on the back are the same groups as the three on the front. Is anybody asking about exam 2 from fall 2017? It must be the other class. Bless you. Because the problem is when you ask me about a specific problem, then I got to look it up. Now, one thing that was asked is there is a problem where I did this. I said R2-bromo butane plus OH minus, and I asked for the mechanism of that. Which means you have to draw the structure of R2-bromo butane with a bold and dashed wedge. So you would go 1, 2, 3, 4, bromo, there's a hydrogen there. So then in my tetrahedron, what I would have to do is, I like to put my bromine there. I like to put my leaving group in that position, because then the OH minus is just going to come in and attack it there. You could go underneath too if you wanted to, but I just like to put the bromine there, and then I like to put the H in the fourth position so I don't have to mess around. So then to make it R, this is number 1, the ethyl group's number 2, and the methyl group's number 3. So if I want it R, I want it clockwise, which means the ethyl group would have to go here, and the methyl group would have to go there to make this the R configuration. And then once I made it the R configuration, then I would react it with hydroxide. So they asked will we need to know how to draw the structure from the name that is given? From question number 2 in the practice exam. These are real exams that people took, but they serve as practice for you. I didn't get these from anywhere. I didn't draw these up as practice. These are the real thing. And then if so, how do we know which groups to put go on the wedges and dashed lines. You want to draw the structure so it turns out to be R. And then you would go ahead and do this reaction. We'll ask you to do something like that. I think I ruled it out this morning, which I probably shouldn't have, but I think we have enough. Could I ask you the problem without the name? Oh, absolutely. So, and if I put bold and dashed wedges in, that means you have to show the stereochemistry in the transition state and in the final product.
Can we just make a quick list of every concept that's on the test?
Every concept that's on the test? I think there was a list on Piazza and then I added to it. But so we're starting in chapter 6, right? So R and S, determining whether a molecule is E or Z. Definitions. Definitions of what? Things like enantiomers, diastereomers, meso, etc. Etc. being then what else? What else did we talk about with enantiomers and diastereomers? We talked about what's the only physical property difference of enantiomers? Right, the polarized light. So they either rotate positively or negatively, plane polarized light. That's what's different. They rotate in opposite directions. What's a physical property difference between diastereomers?
They have lots of different differences.
Like everything. Everything's different because diastereomers are two different molecules. So those kinds of concepts that we talked about with enantiomers. Same diastereomers, enantiomers, etc. Those problems that we have done a couple of today. That's probably the end of chapter 6. Chapter 7 with SN1, I'm going to ask you to draw a mechanism. I'm going to ask you to draw the products without the mechanism, or without the graded mechanism. So in other words, if you need part of a mechanism to write the product, that's great, but I'm not grading it. I'm just looking for the final products. So both the mechanism and the products. For SN2, we have same thing. We've got mechanisms and products. And then we should probably know what makes a good leaving group, what makes a good or poor leaving group, and we should probably know what makes a good or poor nucleophile. I would say the molecule where you have two reactions, which one's faster, slower, same, but I think I'm going to hold off on those. And we're going to start next week on rearrangements. We'll talk a little bit about that, then we'll go into E2. The chapter after chapter 11 is everything together, a lot of what we've done. So chapter 11 is going to kind of be a review of all four mechanisms. I think that's it. E1 mechanism, E1 products. So yes, E1 as well. Anything else I'm missing?
too? Do we need to memorize like which ones are which and if the English or are you guys not gonna give us a
No, I'm not going to give you the table. You'll have to remember the table. Whether you need to flat out memorize it or not,
Okay.
we've talked about some of the features that would let you regenerate that table if necessary. So I would know the features as opposed to just, flat out memorizing it. But whatever floats your boat, that's what you need to do.
Did you just write the products for that?
Yes. So either write the mechanism or write just the products. Oh, the products?
Yeah.
Okay, here's I upload the notes that I do in class at the end of each day. If you didn't know that, okay, but I do. That would be the product of the reaction. It goes by inversion of configuration. So that's the inversion of configuration product.